All right, so you got Rolle's theorem down to your notes. Now, just a quick idea, just kind of visualizing what's talking about here. Notice it's talking about where we know that we have 2 points. This is what the A and the B are. And it's talking about, okay, if we can know that the function between them is continuous and differentiable between them, and so that just means that there's no holes or anything like that in between them. There's no vertical tangent line, no asymptote, all that kind of stuff. We know that if f of a equals f of b, that is, they both have the same y value, they're at the same height, that somewhere between them, the derivative will be 0. Do you see why that would hopefully just kind of make sense? Because if the endpoints are at the same height, then it means that at some point between them, at least one point between them, here in this drawing it's 2 different points, it has to have a horizontal tangent line. You know, it kind of follows, right? And so it could do kind of like that graph that I just sketched for you. That's one way it could happen, where it had multiple. It could just be one big curve going between them. So it could look like that as well, where here we have a horizontal tangent line. It could be even just where the whole thing is horizontal and the whole thing represents a horizontal tangent line. That is a derivative equal to 0. All of those are possibilities. All right, so if we're going to answer this question here, there are 2 different parts. And the first part is that verify part. Verify that the function satisfies the 3 hypotheses of Rolle's theorem on our interval. And so for this part of the process here, that means we're going to be showing that each of these 3 is true. Now for the first one, f is continuous on our closed interval. Well, this is a polynomial function. Is that continuous between 3 and 8? Yes. How do I know? Because every polynomial is continuous throughout negative infinity up to infinity. Its domain is all real numbers. It's everything. And so, yes, it's continuous. Now, since it's continuous, that makes answering the second part about if it's differentiable a little bit easier as well. Because for something to not be differentiable, it could have a hole or a vertical tangent or an asymptote, some sort of a discontinuity basically, or they could have a corner. Okay. Is this graph going to have a corner? No. Basically, the only way we get corners or jumps or, well, corners or jumps at least, is if we have a piecewise function. The only exception there is absolute value, but absolute value is basically a piecewise function anyway. Does it have an asymptote or anything in it? No, because we're not dividing by x anywhere along the line, so I don't even need to worry about that. And it doesn't have a vertical tangent. That only happens with a few things like cube root and some things like that. And so we can know then that it satisfies 1 and 2. What do you need to do for 1 and 2 in terms of showing your work? Nothing to show. You just need to actually check it, but you don't have to write out some big written explanation about proving why it's continuous or differentiable. The third part, though, we can show a little bit more, because the third part is asking us to be able to say that f of a equals f of b. So in this particular case, then, that means I need to be able to show that f of 3 equals f of 8. So let's go ahead and figure out, what does f of 3 equal and what does f of 8 equal? So when we plug in 3 into our equation up here, plug in 3, we end up getting 6. For f of 8, I plug 8 into the original equation as well. Plug it in for x, plug it in for x. You should find that f of 8 equals 6. Good. They're both the same. Yes, you actually want to show that fact. But that means that we can actually use Rolle's theorem now, because we showed that it's continuous, it's differentiable, and both of those have the same y value, the same f of x value. So Now I can go ahead and use that information. That means I'm going on to that second part there where it said then find all numbers C that satisfy the conclusion. The conclusion is that somewhere in there, somewhere in this interval that we are given, the derivative equals 0. So, let's find out. Let's actually do it. So that means I'm going to have to find the derivative first. So, find the derivative. What does f of x equal? Or I'm sorry, f prime of x equal? And we find that the derivative equals 2x minus 11. And Rolle's theorem says that it's possible to make that equal 0 somewhere along the line. And we want to know where it equals 0. That's what they call C in there, is the point where it equals 0. So you solve that out, and you should find that x equals 5.5. So yes, it does actually equal 0 at some point. Specifically, it happens when x equals 5.5. Go ahead and write down this problem next. And then again, we'll kind of go through it together here and see how do we approach it, what do we need to do. All right, so first part again is that verify part. Does it actually meet the requirements of Rolle's theorem? Well, step one is a continuous. So if I just look at this whole equation here, not even worry about the interval, is this equation continuous across all numbers? No. There actually is a discontinuity in here. Where is that discontinuity?
-2.
Yep, it's at -2. It's what makes the denominator equal 0. That gives us a discontinuity in this case. So, in this case, we know that x cannot equal -2. However, it's not in our interval here. And so we don't need to worry about it. It is continuous across all other numbers, but since it doesn't affect this particular interval, we don't need to worry about it. All right, so then it's not differentiable, of course, at -2. Is it differentiable everywhere else? Yeah. It is differentiable across the -1, 3 there. And so that means we've satisfied conditions 1 and 2 out of Rolle's theorem, that at least for this interval, we're okay. But now the last part. We need to actually check those f values. So I need to know what f of -1 is, and I need to know what f of 3 is. Because in order to use Rolle's theorem, they have to be the same. So go ahead and check them. What are each of those values? If all has gone well with those calculations, for f of -1, you should get 0. For f of 3, you should get 0. So yes, in fact, they are both the same. They both happen to equal 0. It doesn't actually matter, remember, which number they equal as long as they both equal the same number. All right, so now we've proven that it actually satisfies all 3 conditions of Rolle's theorem. So we can go ahead and use the theorem. So now the find all numbers C part of it, that's saying figure out where does the derivative equal 0. Because that was the whole point, is figuring out when does the derivative equal 0. So that means first up, finding the derivative. Okay, I'm looking at this equation and I'm thinking this could be a little bit of work depending on if we can simplify it. Does this particular rational expression simplify? No. Let's check. Because remember, in order to simplify it, what we'd try to do is we'd try to factor the top. Yes. And we'd see if we could do that in order to do it. So let's go ahead and factor the top here. So that would give me adding to a -2, multiplying to a -3. Yes, it is possible to factor that. It gives me -3 and a +1. And that's still all over the x plus 2. So now seeing it factored, can I cancel anything out of both top and bottom? No. That is sad. That's a sad moment for us because it means it's going to be a bit more work going forward. If we could have, for instance, if this was x plus 2 instead of x plus 1 over here, then, geez, this thing doesn't want to write at the moment. There we go. Then we'd cancel those out, and it'd be a much easier thing to actually take the derivative of. But sadly, we can't. And so we're just going to have to work from it. Now, in terms of finding that derivative, you could use this factored form that we just wrote out, But personally, I think it's a little bit easier once we're actually finding the derivative to just leave it as an expanded polynomial. So I'm just going to work from the original here. So if I'm going to find the derivative of that, which rule do I need to use? Quotient rule, yes. It's been a little while for quotient rule, right? Let's see how well you remember it. And so when using quotient rule, remember low D high minus high D low? So we're going to do whatever's on the bottom, so x plus 2, that's low, times D high. So that's the derivative of the top of it. That is going to give me 2x minus 2 minus high D low. So the one on the top stays the same this time, x squared minus 2x minus 3, times D low, the derivative of the bottom is just 1. And that's all over the square of what's below. So we take whatever was on the bottom, the x plus 2, and we square it. That technically is our derivative. Let's go ahead and clean it up a little bit though, just because it's going to be maybe a little bit easier to work with going forward here. So clean that up, please. And so then when you go ahead and multiply things out on the top, this is what you should be looking at. Now the big thing to pay attention to especially is the effect of this minus right here. Remember that has to distribute to everything that was in the parentheses. And so that's why this is a plus 2x here and why that's a plus 3 there. Now that we've gotten to that point, go ahead and keep combining pieces from there. And when I combine the like terms on the top there, this is what I end up with. So my numerator is x squared plus 4x minus 1. And the first time I did this problem, I thought, please tell me I made a mistake someplace. And I went through and I double checked my work to make sure I didn't make a mistake. And sadly, I hadn't, because this is not as pretty as I would really like it to be. And sometimes, though, we do have to deal with the ones that aren't pretty, so this is going to be one of those times. Because now that I've gotten this as simplified as I can, I still need to figure out what makes it equal 0. Well, if I have a fraction like this, and I want to figure out what makes it equal 0, that basically means make the top equal 0. Because 0 divided by anything is going to be 0. And so then I'm going to have to solve this by doing 0 equals x squared plus 4x minus 1. And normally I'd like to be able to factor that in order to solve it. Can I factor x squared plus 4x minus 1? No. And that's why it's a sad moment for us, because since it doesn't factor, I have to use what? Quadratic formula. Yep. And so when we plug into quadratic formula, this is what we're looking at. Go ahead and simplify that down, and you can leave your answer in simplified radical form. We don't have to go into decimals here, and we'll talk about that here in a moment as well. And so here's our work for simplifying and getting our answer there. Our exact form for our solution here is going to be x equals a negative 2 plus or minus the square root of 5. Now remember, we're looking in this problem to see where a 0 exists for our derivative, which is what these two represent, on a particular interval. We're looking specifically at the interval from negative 1 up to 3. Now it could be that both of those numbers, the negative 2 plus root 5 and the negative 2 minus root 5, could be that both of those are possible solutions in this case, possible values of c. Or it could just be one of them. So we do need to know which of them actually fits within our interval here. Well, you got two different ways you could do it. One way is you could do it in your head. The other way is you could break out the calculator and push some buttons. Now I know you can push buttons. So let's see, how would you do it if you're going to do it just in your head? A little bit of quick estimation could work here. Because, like the square root of 5, it's about what, if you're just guessing off the top of your head? Well, you know it's between root 4 and root 9, so it's got to be between 2 and 3. And it's going to be closer to the root 4, so it's got to be closer to 2. So you might guess maybe like 2.2, let's say. Let's just say you're guessing 2.2. I'm not saying that's exact, but it's giving us a guess and a place to go from. So negative 2 minus 2.2. That give us about negative 4.2, right? Is that in our interval? Nope. Okay, what about negative 2 plus 2.2? Would that be in our interval? Well, that would give us a positive 0.2. So yes, that would be in our interval. And so a little bit of quick estimation told us what we could also learn by pushing buttons on the calculator, that the only actual solution here, the only value of C that satisfies Rolle's theorem, is the negative 2 plus root 5. So that is the one value at which we get a derivative that equals 0 within this particular interval. One last note out of this problem. This problem, remember, it ended up being a more complicated problem, mostly just because this up here wasn't factorable. If this had been factorable, it probably would have felt a lot easier. We have to just deal with whatever situation presents itself to us when solving these. And it just happened that this one gave us something that took a little bit more work of using quadratic formula and all that kind of stuff. These problems sometimes will be much more straightforward, like the previous problem.